Good morning, sir. How are you?
Fine. So,
FDP is
how's
going
it?
really well.
Uh, uh, Shall we wait for 1 or 2 minutes?
Sure, no problem. I think the participants.
Be joining.
Sure, no problem. Yes.
Dear participants, a very good morning. And we have Dr. Subha Sharma with us for the lecture. And before proceeding to the lecture, let me first briefly introduce Dr. Subha Sharma is currently working in Triple IT Kota as an assistant professor. She has finished her PhD from NTU Singapore on hybrid free space optical radio frequency communication for future wireless networks. Prior to this, she was associated with the Electronics and Communication Department, IIIT Delhi, as a master student. Her research interests are free space optical communication, hybrid free space optical radio frequency communication, MIMO systems, and spectrum sharing. She has worked for different external research grants from various funding agencies, Ministry of Education Singapore, Airbus Group Innovation Singapore, and UGC India, to name a few. In the course of her PhD and MTech, she has published various research papers in Tier 1 international IEEE journals. Along with the journals, she has also published several papers in reputed IEEE conferences. She has also served and currently serving as a reviewer of various Tier 1 transactions, journals, and reputed conferences, such as IEEE Transaction on Wireless Communication, Photonics Journal, Optics Express, IEEE OSA Journal of Optical Communication and Networks, IEEE Vehicular Technology, where IEEE has rewarded her with a Reviewer Recognition Award. Besides academic and research achievements, she has been an active member of IEEE Communication Society, WICE, Women in Communication Engineering, and IEEE Women in Engineering Singapore. She has also organized and assisted in many events. Moreover, in NTU Singapore, she was also a part of main organizing committee for TEDx Talk NTU and NTU Graduate Tech Fest. So many other achievements in Triple IT Quota are also with her. But without mentioning all her achievements, I would like to hand it over to Dr. Subha Sharma ma'am to proceed to your lecture.
Thank you so much, Amit sir, for the introduction. And I'm really happy and glad that you invited me for this talk. I'm not sure whether I'm in the same, I'm in the alignment with the talk, with the topic of this FDP, but I will try my best to make sure that the participants gain a little bit insights about how the communication is processed and is done among the devices or in any kind for that matter. So with this, I would like to share my screen with all of you. I think, is it visible? My screen is visible to all of you?
Yes, ma'am.
Okay. All right. Then let's get started. Um, okay. So hello and very good morning to all of you. I am Dr. Shubha Sharma. I would like to give my sincere thanks to Dr. Amit for inviting me for this talk. I would like to give my gratitude to all the organizers and people behind the successful functioning of this ATAL FTP. I'm very sure that all the participants are able to gain a lot of insights and knowledge from this workshop. And on this note, I would like to welcome all the participants and I would like them to come on board with me for this flight for 2 hours. I hope that with my talk, you would be able to get few insights and basic understanding of communications. And I would like this session to be very interactive, and I want to keep it exciting. Otherwise, and we don't want to make it boring. And for this, I would like your participation, right? So let's get started. Okay. Then can you all tell me that what is communication? How the communication happens? What is communication basically? What do we call as communication? Can anybody tell? Anybody tell that what is communication? None? I want a few of you to, participate and give your, uh, responses so that it's a bit, alive that we are in the talk. It should not be, one side monotonous kind of a talk. So I want a few of you to, respond and speak. So can anybody tell what is communications? Or everybody is, very sleepy in early day morning and not interested to attend the talk.
Express one's knowledge or his interest to the other one, like that is communication.
That is communication. So basically, you're saying that a communication is like to have interest in other persons, what they are transmitting, and you want them to, you want to hear that, or you want to process that one. Is that what you see?
So so I have one thing in mind. So I just want the others to also empathy or understand my
Understand.
concept.
Right.
So
Right. So communication, in a very simple sense, we can say that communication is sending and receiving information between two or more people, right? I want to send, I want to convey what I want to say to the other person, and I want the other person to receive and process that information, and it becomes a information that he is or the other person is able to understand what I'm saying. All right, that is known as a communication. Like if I'm speaking something and you are able to receive it and understand it, that is a communication. That is simple communication, right? That I'm able to convey and you are able to receive and process, right? So this is communication, and it happens between two people, or it can happen between more than two people, and it can it can be a one way and it can be two ways, right? So now suppose I speak English, right? And you are speaking Spanish. So we are not going to have an effective communication because we both are speaking different languages, right? So how, how the communication will happen? Do you have any idea like how the communication happens when the two persons are speaking different languages? How will you understand the other person speaking some other language? Anybody? What will you do if you meet somebody who is speaking some other language? How will you communicate with that person? What will you do?
sign languages.
Sign languages. But sign languages are for those who are deaf. They are not able to speak. But in when we are able to speak and when we are able to convey, it's just that we are not able to communicate in the same language. So what we can do, we can use certain guidelines so that we can understand each other, right? We can use a translator, or we can use a dictionary, or we can try ourselves to somehow adhere that what other person is speaking by translating that information or whatever he is speaking. So that means that certain guidelines are required, or certain translation or certain processing is required when the two persons are speaking in different languages. So we can say that certain or set of rules or conventions are required to communicate when two persons are speaking different languages, right? So from here we get that for communication, a set of rules and conventions would be required if two people are having different languages, right? So now, here is the question that there are two computers at two separate locations, or there are two devices in a separate locations. Now, how do these devices and computers communicate? How do they communicate? How are we going to make a connection between these two and how they can communicate? Anybody? Simple and basic question that how you all know that when you transfer the file from one phone to another phone, or you are doing something, or you're transmitting something, you require something to transmit from one computer to another, or one mobile phone to another. So you have a little bit basic idea that how the devices and the computers communicate, right? So can anybody give any kind of response that how the devices communicate with each other? You have a little bit of idea. You can just try that how the two devices communicate. Anyone? Anyone? No idea that how the two devices or the two computers can communicate? Okay, so let's see that any two computers or any two devices, and especially we can take an example of two computers. Suppose they are lying next to each other. All right, so in the most basic form or the simplest method to communicate or to connect the two computers without any internet, right, without using any internet, is through an Ethernet cable. Just connect them with a LAN cable, right? And they are having the network interface cards, right? Now, once these are connected with the LAN cable, connection is established. Now, these two systems can share files between them, and then they can view and edit those files, right? But now suppose if one computer is working on Windows and another one is working on and has a Mac OS installed in that computer. Now what is happening here? Now what is happening? How these are going to communicate with each other? Now this is a similar example, right? This is a similar example that now one is speaking English and another one is speaking Spanish, right? Here one has Windows installed on it, another one has Mac installed on it. Now you cannot connect these two with a LAN cable. They are not going to share the files, right? They will not be able to share the files. They will not be able to communicate with each other because they both are speaking different languages, right? So how you are going to connect these two? How you are going to communicate? Because I want to communicate with the Mac phone. If you have Apple phone, if I have Android phone, I want to communicate with you. It does not matter if you have an Apple phone and I have an Android phone, and then it doesn't matter, right? Because I want to communicate with you. So having different languages should not stop us to communicate with each other, right? We can make a communication link. We can connect with each other. So how does that work? So similar to what we were thinking, that to connect when we are speaking different languages in a computer's world, also to connect when we are having two different operating systems installed in our computers, what we will have to do, right, to accomplish a successful or effective communication between computers and devices, if they are, or they are having different OS, or maybe they're having different same OS, what we have to do, we have to follow a set of rules. For example, one system is some other network, another system is in another network, but we want to communicate, right? We want to connect. So for that, we have to follow a set of rules and conventions or certain protocols to have an effective communication. And if we are following those set of rules, or if we are translating ourselves, then we can communicate with each other, right? And if we are following those rules, then those two systems, lying at a very far end from each other, they are not connected through any kind of cable, but they are just connected to the internet. They can communicate with each other, but they have to follow certain rules, conventions, and protocols to connect with each other, right? Now, therefore, we use, if we are having systems or we are having devices which are far away from each other, we have to use internet or certain, a network to make the communication happen, right? So therefore, we use internet and the communication protocols together with it, that is the set of rules and conventions to have or to achieve successful communication. So what we do, for example, on my system, I want to use applications like Chrome and Firefox. Okay. I want to use the applications like Chrome and Firefox. These are your web browsing, your web browsing applications. You want to browse the internet with this thing. You want to browse something, you want to search something. You can do anything with them, right? We use, Skype and emails for video and audio call meetings. So now all these applications must follow certain protocols to get connected or to transfer the data. For example, the Chrome and Firefox are applications, so they are the network application. They are running in your PC for web browsing, and they follow HTTP and HTTPS for the web browsing. So these are the protocols, that is HTTP and HTTPS. These are the two protocols they follow for web browsing, right? So we have to follow certain protocols to have a communication or to transfer our data. Now, not just web browsers, any applications, we are bound to follow protocols and functions, right? And there are dozens of these protocols that enables various functions in the applications for the data transfer. Okay, so there are various such protocols which enable all these applications for the transmission and reception of the data. And these protocols forms the basis for various network services. Right? So with these protocols already defined, they form the basis for the various network services. Like, so if I want to do the file transfer, with these protocols we can actually do the file transfer, right? Then for the web surfing, okay, so these protocols also enable web surfing. They also enable the emails. You can send and transmit and receive the emails. They also work for the virtual terminals. For example, the file, a file transfer is enabled by the FTP protocol. Web surfing is done when you're doing web surfing. The web server, that is your Chrome and Firefox, are following these protocols for the web surfing. Email follows SMTP protocol, and virtual terminal, they are following telnet protocols for the video conferencing and video streaming. So therefore, we can say that these protocols help enable the user activity. Right? Are you guys with me? Are you able to understand? Is there any issue you're not able to understand? That okay, you have your PC, you are using certain kind of application. So basically, in the background, these applications are following certain kind of protocols, right? Is there any issue with this? Is anybody here? Are you able to not follow? Are you able to follow what I'm trying to say? Okay, so let's move forward and then let's see that okay, we are using any application on our PC, and that application is following certain protocols for the data transmission and reception. Now, after that application, we have, suppose we are typing hi on WhatsApp, right? Now, hi on WhatsApp is converted, or it is in the form of characters or numbers which we want to transmit, right? And these numbers must be converted into machine understandable binary format. Okay? So if I'm typing hi, my machine does not understand that what is hi. What it understands is a binary stream of binary format, a bits. It can understand bits. So what we have to do, we have to convert these characters into a stream of bits. Now, when we are converting these characters into a stream of bits, what it is known as translation. Right now, we have translated. If I'm speaking Spanish, I have translated it into a breach of stream of bits. Now my machine can understand that language. Now this translation is done. Now before transmitting these bits, what we want these bits to be reduced. These are long stream of bits. I want to reduce it, and this reduced bit can also represent the original data. Okay, and this bit reduction is known as data compression. So if I have a long stream of bit, what I have done, I have compressed that long stream of bits into a short stream, and this compression is known as data compression, and it can be lossy and it can be lossless. It can be lossy and it can be lossless. Now I'm done with my data compression. Now, as the file is reduced, now you have done the data compression, your 5 MB file is reduced to a 2 MB file, right? Now it is going to use less space, right? Less space in your computer and less space in the network, right? So now what can happen is we can transmit and we can receive this file in a very less time, and do this in a very less time comparatively, and that is the data transmission can be done faster. So data compression helps us to achieve faster data transfer. It can help us achieve faster data transfer, and it is very important when we are talking about video and audio streaming, right? When we are doing a real-time audio and video streaming, we want the data transmission to be very fast, right? So data compression is very important for the data transfer to make it fast. Now, apart from the translation and data compression, what we want the security of our data as well, right? So to maintain the integrity of the data, that the data does not get corrupted, and to make it more secure, what we do encryption. Encryption of the data enhances the security of the sensitive data. If I am sending any sensitive email, I want it to be very secured, right? And therefore, we enable the encryption of the data. So we know that now the WhatsApp messages are also encrypted, right? So nobody else will be able to decipher your messages, even in anywhere, because your messages are encrypted. Now, only the sender and the receiver to whom those messages are conveyed can only see those decrypted messages, and nobody in between any link can see what is being sent. So you can say that your WhatsApp calls or your WhatsApp messages are more secure than the normal calls and normal messages, right? Because they are encrypted. Now, the encryption, what it does is it enhances the security of the sensitive data, and the sender side data is encrypted, and at the receiver side the data is decrypted. And the SSL, or the secure socket layer protocol, is used for encryption and decryption. So just encryption and decryption is done by this SSL protocol, and done. Now encryption is done. So you have now a bit stream with encryption. So you have encrypted bit stream with you, right? So you have a bit stream which is encrypted. Now, apart from the translation so that the machine can understand, then we have compressed the data to make it faster, and then we have encrypted it to make it secure, right? Now what you want, I want to make it more reliable communication. I want it to be very reliable. Now, to make the communication reliable, we have to attach it with certain things so that it, the link and the transmitter and receiver knows that where to send it. Right? If I am transmitting it, I should attach it with things so that it knows where to send it, right? So that the communication is more reliable. And to do that, what we do is this can be done by segmentation, and together with that we do the error control and the flow control. So all these things happen, right? So in the segmentation, the data which we have, that is a strong, a long stream of bits after encryption, what we will do is we will segment this data. We divide this data into small data units. Okay, so now the long stream of bits is divided into small data units. Okay, and each segment contains a, now these are known as segments. That long stream of bits, you cannot send a long stream of bits as it is, right? You have to patch it with something, right? So we have divided that long stream of bits into data units. Now data units mean what we have added a port number. Now what will port number do? And together with that, so port number helps to helps each segment to to relate it or to resemble the segments with the correct application. So we'll see, and together with the port number we also add a sequence number to it. Okay, so what will port number will do? Port number helps each segment to the correct application. So the port number will tell us that for which application this data segment is for. All right, and the sequence number helps to resemble segments in the correct order. Okay, so the sequence number tell that it is 1, 2, 3, 4. Right, so you have to at the receiver side it will be 1, 2, 3, 4. It's not like it's 4, 3, 2, 1, right? So we have to make it in the sequence so the data can be reconstructed at the receiver in the same sequence it was transmitted. So sequence number is very important to make it in the same sequence as it was transmitted at the transmitter side. So this is how we have segmented the data. We have added the port number and the sequence number with the data to make sure that it goes to the application it was sent for and it is in the same sequence with which we have transmitted. Now what we want to control? We want to control the flow as well, right? So what is flow control? Flow control is the amount of data being transmitted, right? So for example, I want to transmit the data. For example, let's consider that we have a mobile phone. That mobile phone is connected to a server. Okay. Now, server can transmit the data at maximum of 100 Mbps, and the mobile phone can process the data maximum at 10 Mbps. All right. So now when we are downloading certain file from the server is transmitting starts transmitting at 50 Mbps, right, which is greater than the rate of our mobile phone. Okay. So it is transmitting at 50 Mbps, but the rate of the mobile phone is only 10 Mbps, right? So what will happen? So now if we are transmitting at different speeds, so what will happen? Now how the flow control is done is that mobile will send a signal to the server that lower down the data rate to 10 Mbps. Right? So now the server will lower down the data rate to 10 Mbps so that no data gets lost. Right? Now similarly, if a server is sending data at 5 Mbps, right, sending at 5 Mbps, now mobile can tell that, this is very low data rate. You can actually go up and you can transmit at the 10 Mbps. Then the server starts transmitting at 10 Mbps to maintain the system performance. It should not be a very low data rate system. So to maintain the system performance, the flow control is done. And this is very important to control the flow of data so that no data gets lost and the system performance is also maintained. All right, so this is how we have controlled the flow. So we have maintained we have done the segments. We will transmit these segments. We are doing the control of the flow of the data. Another thing we want to control is the error. So now let's see how the error is handled. So suppose if we are transmitting these data segments, and these data segments we have transmitted from the server to the mobiles, but one of the data segment is missing. One of the data segments is missing. So what will happen? We will do automatic, what will be followed is an automatic repeat request. So mobile will send an automatic repeat request to the server to retransmit it, because I have missed it. I have not received that data segment because the sequence number is missing. So the mobile knows that, okay, the sequence number is missing, so I want the sequence number back. Right? So automatic repeat request, what will happen? It will retransmit the lost or the corrected data. Right? And together with this, to control the error, what we add some checksum bits to it. All right. So these checksum bits are added to find out whether the received segment is corrupted or not. So these checksum, some extra bits are added to process whether the data is fine or not, or whether it is corrupted. Right? So these checksum bits can also tell that the data is corrupted. If the data is corrupted, then automatic repeat request is sent from the mobile side to the server to retransmit that data segment. All right. So now we have done with the control. So here what we had done what we had done is that we have done the flow control, we have done the error control, and we have done the segmentation. Okay. So now after the segmentation, now we have data units with us, right? We have data units with us. Now these segments are the data units. Now we have these segments at this moment with us. Now these data segments must be transmitted from one computer to another on different networks, right? So can anybody tell me, or can anybody guess that how we transmit these data segments from one computer? I'm sitting, for example, in Jaipur, and I want to transmit these data segments to US, in New York City, US, right? How these data segments are going to get communicated. So I'm connected to my network, which is network 1, and the other person in US is connected to network 2, right? Or so how these data segments which I'm transmitting are going to take the path, how they are going to flow and reach to that network and a person who is sitting in US. So how these data segments must be transmitted from one computer to another located in two different networks. Can anybody guess how this is going to happen? Anybody can give me any idea, or it's a simple guess that how can this happen? Anyone? Okay, so probably can anybody tell? Yes, Vinay. Renuka.
I think it is basically by IP practice.
By the IP address. Correct. Very correct.
Yes.
Thank you, Renuka. So yes, she's very correct that what we have now, So these data segments which I want to transmit, so I am in network 1 and another person is in network 2. Now what we will do? We will transmit the data using the IP address. That's correct. So segments cannot be transmitted as it is. They must be converted into packets, right? So now we will transmit the data from network 1 to network 2, and they must be converted into packets, right? And these packets are what are these packets? These packets, so router, so we will be using these routers, right? Routers for transmission and reception. And here we will do this logical addressing, right? Now we will attach the address to it. Like when we are sending any letter to somebody, we write address on that, right? So now here in the computers also, when we are transmitting something, we write address to it. So when we have a data segment, we want to add the address to it. All right. So for the address, what we have is IP addresses, right? So IP address of this device is added with the segment, right? Now, and this IP addressing is known as logical addressing. This IP addressing is known as logical addressing. Now, so every computer has its own unique IP address. All right. So it has a unique IP address. It has IP1 and it has IP2. Now, these IP address of the sender and receiver are assigned to each segment. Okay. So these segments are assigned with the IP addresses, and therefore, after assigning the IP address, these segments are converted into packets. So each data packet reaches the correct destination using the IP addresses. So now these segments are attached with the IP addresses. So we have written the address on the over the letter, right? We want to send a letter to somebody. We have written the address over the letter, right? To and from, right? So this is to and this is from. Okay? So we have done the logical addressing here to send the data over the network. And these segments together with the IP addresses are known as packets. Okay, now we want to send these packets to the other network. How these packets are sent to the other network? For that, we will have to do routing. Okay, and we want to do the path determination. Now this packet is sent to network 2. For that we will have to calculate the route, that through which route we will be transmitting that packet, and how and which path to take to transmit these packets. All right. So now how the routing is done. So routing is a method to move the data packet from the source to the destination. Okay. Now it is based on, as Renuka suggested, on a logical address format of IP addresses. So we want to attach IP addresses to it and then transmit the data packet from the source to the destination. Now suppose I am, computer A is connected to network 1. Okay. So computer A is connected to network 1, and computer B, which is connected to network 2, I have requested to access facebook.com. So I'm sitting at computer B and I have requested to connect to facebook.com. So now how this facebook.com is going to send and receive, how computer B is going to receive the data from facebook.com. So now there is a reply from the Facebook server. So this is for example a Facebook server. It is going to reply to computer B in the form of packets, right? So it is going to, now I have accessed facebook.com. Now the Facebook server is going to reply to me in the form of packets, and these packets need to be delivered only to computer B, right? Not to anybody else, but only to computer B, right? Since in a network each device has a unique IP address, as Renuka said. So it has a unique IP address. So Facebook server has a unique IP address, and sender and receiver have their unique IP addresses, right? So now this IP address is attached with the Facebook data packet. All right. So the packet has this IP address. So packet has the IP address of the Facebook server, which is the sender now, and the IP address of the computer B, which wants to communicate with the Facebook server. So this data packet has the IP address of the Facebook sender and the IP address of the computer B, which wants to access the Facebook server. All right. So now this is your IP addresses are attached to it. Now together with that IP address, what we want to have a mask as well. So the mask will tell us, for example, the mask is 255.255.255.0. So this mask will tell us that first three combinations will tell us the network that from now I have Facebook server is transmitting a packet. But first it should know that which network to go. There are several networks, right? Network 1, network 2. So this first three combinations will tell that which network to go to, right? So this will tell, okay, this is the network to go to. And the third or the last combination will tell us that which computer in this network to go to, right? So this mask will decide that first three combinations are for the network, and these first three combination is for network 2, and the last combination is for the computer. All right. So with this IP address, I'm going to network 2 and to computer B. All right. So this is how your data packet is going to travel from the Facebook server to your computer. So first, based on the IP address, and the mask, the received data packet will move to the network 2 and then to the computer B. So, based on the IP address and mask, based on the IP addresses and mask, we are going to make the routing decision. So this is how the routing happens, right? So we attach the IP address and then we have the mask to it and the routing happens. Then I will be able to connect to the Facebook server, and Facebook server can give packets to my computer. So this is how we have done routing. All right. So what we had packets, and then we have done the routing of those packets. Now another thing is path determination. It is not like path is simple. We have to take different paths to reach to our destination, right? So a computer is connected to a server or another computer in various ways. It can be connected to various ways. It can take any path. It can take this path, it can take this path, and whichever is available based on certain algorithms it is using. Like, so choosing the best possible path for data delivery from source to destination is called as path determination, right? So apart from having packets, routing is done. Path determination is also very important because it chooses the best path or the best possible path to reach to the destination. Now, devices for path determination using various algorithms, for example, open shortest path first, or modern gateway protocols, or intermediate system to intermediate system protocols, and these protocols determine the best possible path for the data delivery, right? So this is how your packets are going to travel from the sender to the receiver. Right? So packets are formed, routing is done, path determination is done, and your packets with the IP addresses can be delivered to the computer. Now we saw the logical addressing. Right? Logical addressing is the IP addressing. So we have written the logical addresses to it. But now I want So we have the data packets with the logical addresses. But now what we also want to have a physical address to make sure that we are transmitting to the right person, right? So our computers or any devices we use per se, for example, mobile phones, any sensor device or any type of gadget we are using, it has an IP address. An IP address is a logical address. It can be changed. It is based on the session which you are currently into. It can be changed over time. But your MAC address is the physical address of the device and it is non-changeable. This address will do your physical addressing, and therefore we add the together. Now this is your data packet, that is your segment, and it has the IP addressing to it. Now for the devices to have physical address, we will add MAC addresses to the together with the data packet, right? So MAC address of the sender and MAC address of the receiver, and this forms your overall frame. So what we have done the logical addressing, and then we have further done the physical addressing, right? And after doing the physical addressing, what we get is known as frame. Now this frame has the IP address. Now it has the data segment which we want to transmit. It has the IP address and it has the physical address of the machine. Okay? Now this MAC address is actually a 12-digit alphanumeric number encoded with the network. It is a 12-digit alphanumeric number. It is encoded with our devices in the network interface card. So every device has this network interface card with which we are going to attach our cable to it, right? And it has a address which is known as MAC address. Okay, and this number is provided by your computer manufacturer. This is embedded by your computer manufacturer. Now, the data unit in here is known as frame. So we have frame with us. Now the data is transmitted in the form of frame. So this whole thing we have to transmit. Now to transmit this whole frame from one device to another, we want a medium, right? We want a medium to transmit. Now what we are coming into accessing the media for the transmission. How we are going to access the media? So the local media includes, copper wires. It can be copper wires. It can be optical fiber cables, or it can be any kind of air, for the wireless transmission or for RF communication. So there can be various kind of media to connect the two systems. So we are coming into the physical link. So we have to make any kind of physical link between the two machines or between the two networks or between the two computers to transmit our data. So we want to transmit this frame. It is made up of a stream of bits, and we want to transmit that through the physical link, which is known as media, right? Now we have done the physical addressing and we have the frames with us. We want to transmit these frames. All the addresses are written on the frames, and these can be transmitted using a physical link. And physical link can be copper wire, LAN cable, it can be optical fiber cable, or it can be a wireless network, and we just transmit in the air using the RF communication, right? Now how, so we have the media with us, we have these copper cable, wire or air with us. Now how do we access the media, right? We access the media, we want these frames to be transmitted, so we want to access the medium. Now the controlling and data placement and error correction has to be also done, right? Now how to control your data frames, how do we control it to access the media, and in which possible or the best way do we place our data in the media. And together with that, we also want to detect the errors which are going to happen due to the transmission over the medium, right? So now let's consider two distant hosts. Right? We have two distant hosts with us. One is a desktop, right? One is a desktop and another one is a laptop. These two has to communicate with each other. Since the computer and laptop are connected to two different networks, these are on two different networks, it requires IP protocol to follow for the communication, right? So we know that we have to attach the IP address, we have to attach the MAC address with us, with the data segment for these two networks to get connected for the communication. Now, in this example, the desktop is connected with router 1, right? It's connected with router, IP with router 1, and it is connected via a Ethernet cable. So this desktop is connected to router 1 with the Ethernet cable, and we want to connect the router 1 with router 2 using a satellite link. To connect it to the satellite link, and the laptop here is connected to router 2 using a wireless link. So here, suppose for example, this router 2 is your Wi-Fi router, and your Wi-Fi router is connected to your laptop with a wireless link, right? It is transmitting in the air. Now, the MAC addressing is added with the IP packets. So we have the IP packets with us. These IP packets we want to transmit. So we add the MAC addressing and the tail with this link. Right? We add the MAC addressing and tail is added with the IP packet, and it is now converted into a frame. It is converted into a frame. And these frames are actually the Ethernet frames in this case because of the Ethernet cable or the LAN cable. So these frames are going to follow the Ethernet cable addressing to reach the router. So now the R1 is going to receive the frame and decapsulate it, right, to the IP packet. It has received this frame and has decapsulated with only the IP packet. Now, the R1 is going to attach its own MAC address and tail with it. It is going to encapsulate it again into a frame so that it can cross the satellite link. Right? It can cross the satellite link. Then it reaches to the receiver or a router R2 using the satellite link, and it is decapsulated into a IP packet at router 2. Now router 2 is again going to encapsulate it with the wireless data link frame. Okay. It has also added the address of this computer and some extra bits as a tail for the error detection together with the IP packet so that it reaches here. Right. So this is transmitted here. It has decapsulated, added the addresses so that it cross over the satellite link. It is reached here, decapsulated into a IP packet. Then again H3 and T3 are attached to so that for this wireless link, and now it can reach the laptop's network interface card using this address, and this IP packet can reach the laptop using the wireless link frame. And now here it is again decapsulated, and then what we get is the IP packet what we had transmitted from here. So we get the IP packet here for further processing. And finally, the data arrives to the application with which we wanted to transmit. So for example, I transmit high here. So now the high is received here, right, into the application. So this is how the data is transferred from the computer using this link to the destination, right? To the destination. So it has to be transmitted in the form of frames. Right? So the IP packet is attached with different MAC addresses, and these MAC addresses changes time to time in the communication link, but the IP packet or the IP address remains same because that IP address is of these two machines. But these MAC addresses keeps changing as the machine, as the MAC addresses of the upcoming devices comes. So H3, H1, H2, H3. so many MAC addresses are added and encapsulated and decapsulated so that the IP packet is received by this router. All right, so that is why we do physical addressing, and this is how the media is accessed by adding the MAC addresses, encapsulating and decapsulating the packet again and again to be received by the destination in some other network. Now, so any doubt to anybody? Any doubt here? Is everything clear to you? How the media is accessed, how the frame is made, why physical addressing is done, and how using the addressing we are transmitting the data packet. Any doubt to anyone? Can ask. It is better to ask the doubts now so that we can go in align with, and I'm also sure that you guys are able to understand what I'm trying to tell. So any doubt to anyone? No one? No doubts? Everything is clear? You can say yes or no also. If you don't have any doubt,
Actually,
you can just
I have doubt. I have a doubt, and I done a
tell.
question in chat box, ma'am.
Oh, in the chat box. You can speak. Actually, I'm not looking into the chat box right now. So you can just speak whatever doubt you have. I'm going to answer them.
Actually, IP address is belongs to system or network, ma'am.
So IP address is actually a system address, not for the particular system. It is for the network, right? It is made actually. It is particularly will be for my system, but it will be changed. It will be changed if I'm going to connect to a separate network. For example, I'm sitting in my home and I'm connected to my Wi-Fi. So I may have a different IP address here in this network, but if I go to some other place and connect to some other network, then I might have a different IP address. All right, so the IP addresses change according to the networks for the devices.
Okay.
Right?
One more doubt, ma'am. Performance is done on which layer, ma'am?
All right, so performance is basically done on any layer you can do it, right? In physical layer, you can do the performance in terms of bit error rates.
Actually,
And
ma'am, I mean, which frame is converting on which layer?
which frame is converting on which layer. See, the frames are made only in the back layer or the data link layer, where we are. So till the network layer we had packets. Now we are adding what we know as the MAC addresses to it, and then only the frames are getting converted, right? So now the frames are at the MAC layer or the data link layer, and these frames are we are going to transmit to the physical link. We are going to access the media, that is any wireless or any media, and these frames are going to travel through the media. So these frames are getting converted in the media MAC layer or the data link layer. Am I able to reply what you are saying?
Sorry, ma'am. Actually, I am not getting your voice, ma'am.
You are not getting my voice. Okay. So what I'm trying to say is that, so we had the IP packets, right? Now these IP packets are encapsulated with the MAC addresses. Now we have the MAC addresses of the sending machine and the receiving machine. So MAC addresses are encapsulated with the data packet in the MAC layer. They are encapsulated, and then now we transmit it with on the path in the MAC layer, right? Now the path determination is done, and the MAC, the packets are transmitting using the MAC address in the physical link, using a physical link or using any media, which could be air or which could be any wired media, right? Is it clear to you now?
Yes, ma'am. Now clear.
Okay. All right. So now we have access. Now, anybody else has any doubt? Okay. Now, assuming that nobody has any doubt and everything is clear to everybody, Can everybody tell me that yes, it is clear to us?
Yes, ma'am. Yes, ma'am.
Okay, good. So now, since the framing is clear to us, that we have made the frames, and now we are transmitting these frames. Now, how these frames are. So now we had the data from at computer and at the laptop. This data is transmitted from computer to laptop using these mediums, right? These different mediums. Here it was Ethernet cable, here it was a satellite link, and here it was a wireless link. So we have changed the MAC address according to different machines, right? For this, there was a different MAC address. For this, there was a different MAC address. For this link, there was a different MAC address for this link. So the MAC address was changing, but the IP addresses remained same for the two networks, right? Now, how is the data placed and received from the media? Right? How we are placing this data? So there may be, number of devices connected to a common medium, right? There may be number of devices that are connected to the common medium. For example, there is one router and there are many number of devices that are connected to this particular router. So now if all these devices send the data at the same time, there is a possibility of collision of messages, right? So there will be a possibility that these messages collide with each other, resulting in a useless message. So there now this message is useless. We don't want this message. So such message can neither be understood by any of the recipients. So if this is a useless message, none of the recipient are going to utilize this message or understand this message, because this message is now collided. Now, to avoid such situations, what we must do? What is to be done? So for this, we need to keep an eye on the media, right? We have to see when the shared media is free. Whenever it is free, right, then only our device can transmit. So that there is no, so that the data is received by the destination or the receiver without any collision, right? So for that, what we do is we do carrier sense multiple access, right? So the carrier here is media. Media could be a LAN cable, optical fiber, or it can be air. So these media to which we want to transmit, we have to do a carrier sense multiple access. That means we have to check whether the media is free or not. Whenever it is free, all right, whenever it is free, we can transmit the data without having such collisions of data. So this is how the data is placed in the media. Okay? You have made the packets, you have made the frames, but you don't want those frames to get collided with other frames. So for that, what we have to do, we have to sense the access, we have to sense the media again and again. And whenever it is free, then only we can transmit or we can access that media. And thus, in this way, the transmissions are controlled. Right? Now, we also see that this tail is also added together with our packet, and here we have MAC addresses, but we are also adding this tail together with in the frame. This tail is actually certain number of bits which are used to detect error in the received frame. All right, so there will be a sequence of bits, and at the receiver side it should be the same sequence of bits which will tell us that the received frame is received correctly. If this is corrupted, that means the whole frame might get corrupted, right? And the error can be detected using these tail bits, right? So this is how the media, we access the media using the carrier sense multiple access, right? And these tail bits are used to detect the errors when your data packet or your whole frame is received at the receiver side. Now, error, why these error occurs and why do we have to attach the tail bit? These errors occur due to the certain limitations in the media, right? When we are using the media, for example, air, right? So we are transmitting in wireless air. Now, air is your channel, but it has certain limitations. For example, It can distort your signal. It can, add noise to your signal. It can, you know, have different implications of this channel for on your frames or on your signal, which can, add errors to your overall frame. And that is why we add these last few bits in the frame to detect the errors at the receiver side, whether your media has affected your data frame or not, right? So these these tail bits are very helpful in detecting the errors at the receiver side. All right, so this is how we have accessed the media using the MAC addressing, right? And after the MAC addressing, the media has we have accessed the media, but how do we place and control our data is done by carrier sense multiple access. That means we have to keep an eye on the media, and whenever it is free, then we can transmit. Together with that, we add a tail of bits in the frame for the error detection. Whether the frame is received perfectly or not, the tail bits can tell us. Now, all right, so let's look into it again. So what we had, so the sender wanted to send certain data, right? So that data we have converted into a segments, right? Now these segments are actually, we have converted that into a packet. So we have attached source IP and destination IP to it. Now these segments or these packets are converted into frames, right? Now this is a frame. So here we have added source MAC address and destination MAC address, and this is FCS, that is the checksum bits or the tail bits we have added for the error detection. All right, so this is the frame with us now, right? This is a long bit stream. Basically everything is a bit stream. The source MAC address is in the form of bits, destination MAC address is in the form of bits, packet is in the form of bits, your checksum is also in the form of bits. So everything is a stream of bits, right? So this is a bit stream. Okay, now this bit stream must be converted into signals, because we cannot transmit the bits directly. Bits are understandable only by the machine. Bits are understandable only by the machine. Now we have to transmit it in the media, and media does not understand bits. Okay? So machine has the language which is in the form of bits, but medium does not have that language. It speaks into some other language. So we have to convert these bits into the language which media can understand, right? So there can be different types of media. So now when we want to transmit these bits, we have to convert it into the form of signals. Signals which media can understand, right? So signals can be, so there can be a digital signal. So what we do, we convert these bit stream into form of a digital signal. Right? So digital signal can be, a voltage form. Okay, for 010101 can be in the format of voltage. And this stream of signal can be transmitted over a copper wire, over a wired media, right? So it can be transmitted over a copper wire or a LAN cable. Okay, so they understand the digital signal. Now, in case of light, or in case of optical fiber, if you want to transmit your signal over optical fiber can only understand light. Right? So your stream of bits must be converted into light waveforms to be transmitted over optical fiber. So these stream of bits are converted into light waveforms to be transmitted over the media. Okay. Now, another one is your air. If you want to transmit your data over the air, what you want? You want radio signals in that case. So your stream of bits are converted into the RF signals, right? And RF signals require the conversion of the digit or the bits into the analog signal waveform. And in the air, you can only transmit the analog waveforms. Okay, so signal is generated depend on the type of media you want to transmit these bits. So now, finally, at the receiver, the data is received in the form of signals, right? Data is received. Now, media is accessed. I have transmitted over any of these three medias or any of the media for that matter. And then after coming from the media, what you will receive at the receiver is again signal. For example, I am transmitting with a LAN cable. So LAN cable, I had transmitted these signals, digital signals. What I will receive at the receiver side, if it is I'm receiving through a LAN cable, then I will receive the digital signal, right? Now this digital signal is again converted into bits, right? Is again converted into bits. Further, it is converted into frame again. It is then converted into a packet again, and then it is converted into a segment, and then the segment is received by the application which we were accessing, for example, Facebook, right? So this sender had sent the hi from the Facebook. It has been converted into a segment, packet, frame, bit, signal. It has accessed the media. As signals are received, then it is converted into bits, frames, packets, segments, and then the hi is received at the receiver side. So this much processing is being done in order for your hi to be received from the sender to the receiver. Right? Is it clear to everybody how the communication of your hi is transmitted and how it is received at the receiver? Okay, clear to everybody? This is happening in the, so this whole thing is basically your physical processing, right? Till here it was Mac processing, and here this is all physical. So this comes into your physical layer where you transmit the data, you transmit your bits in the form of signals, and when the signals are received at the receiver. So this whole thing, this from signals to signals is your physical, right? Because you're accessing the physical media. So are you able to understand this? Is there any doubt here? Any doubt here? Everything is clear. It's in the sequence, everything is clear that how your data is transmitted and how it is received at the receiver side. Any doubt to anyone? Any doubt? Instead of writing in the chat box, you can speak here. I have no problem because I'm not going to into the chat box right now. I might do it at the end. Any doubts to anyone? No doubts. All right, then we will move ahead a little bit. So again, so now what we had done, we have the copper wires, we have light signals, we have air, and the data is transmitted through these media, we know. And we have the wireless data transmission where your data is transmitted wirelessly. This is what we do generally in terms of when we are talking about device to device communication nowadays. So what happens, we do this kind of wireless transmission of signals, and then it's again received in the form of segments to the receiver. So now talking about all the system of the communication, the whole process, how your data is transmitted and received, we also must look into the signals which we are transmitting. So we are transmitting, what we have is digital signals, and then these signals, when we look into spectrum of these signals are having infinite bandwidth. So when we are accessing the media has to have that infinite bandwidth in order for our signals to be transmitted and received in the same manner which we want. But unfortunately, the media does not have that kind of infinite bandwidth. These are having channels. So these media is having a certain bandwidth, and we have to use this bandwidth to transmit the data. So when we are transmitting a digital signal and the bandwidth is limited, your channel, your media is having a limited bandwidth.
Ma'am,
What?
excuse me, ma'am. Can you explain previous slide once again, ma'am?
Here, this one? This one?
Yes, ma'am.
This one. Okay.
Yes, ma'am.
So, all right. So what we have, media with us. For example, our media is a wired media or it can be a wireless media. Now, if we are talking about a wired media, then wired media has a certain bandwidth, right? It can be of two types of channels. So that bandwidth can be a very wide bandwidth, okay? And it can be a low pass channel with a narrow bandwidth. If it is a wide band channel, that means it can pass large number of frequency components, right? If it is passing large number of frequency components, our digital signal can be passed through this wide bandwidth channel and it can be recovered easily. But if our media is of very poor quality and it does not have a wide bandwidth, it's a very narrow bandwidth kind of a media, right? Then our digital signal has to pass through this narrow bandwidth kind of a media, and our digital signal will be more distorted, right? Will be more distorted. So let's see here. So for example, this is our digital signal. Right? It is passing through a media, and media has a dedicated medium with a finite bandwidth. So all the frequency components of this digital signal will be passed through the media, but what we will receive is a bit distorted form of this signal, right? Because some of the frequency components are not passed through this channel because it has a finite bandwidth, right? So we get a distorted form of this waveform at the receiver, right? The signal will be distorted due to the bandwidth of the media, due to the bandwidth of the copper wire, or due to the bandwidth of the LAN cable, right? So it has, what we will receive is in the form of distortion. But this happens only for bandwidth, transmission having large wide bandwidths. That such kind of distortion happens. If the distortions are if the channel having very narrow bandwidth, what we have to do is we have to convert these digital signals into a rough approximation of the digital signal into the analog signal, and then only we can transmit, right? So I think we should not delve into more details of how it is transmitted. So basically what happens is, when we are transmitting through the media, this digital signal is transmitted into a distorted form of signal which is received to us due to the media imperfections. So media imperfections causing these kind of distortions, right? Now this is for the channels having wired media. When we are talking about wireless media, then we are talking about a band pass kind of a channel which is not starting from here, but it has certain bandwidth in the middle of some frequencies, for example 900 megahertz kind of frequencies. Now if we want to avail this channel, then what we have to do, now we had the bits, now we have to modulate those bits and convert it into a analog waveform. Then only we can access the wireless medium. So wireless means air. Air does not understand bits. Air does not understand your digital signal, your voltages, nothing. It can understand only radio frequency signals. And radio frequency signals are your sine and cos waveforms, right? Are your sine and cos waveforms. So what you have to do, you have to convert your bits into sine and cos waveforms, and then only you can transmit it to wireless medium. So when you are talking about device to device communication in robotics, what you are actually doing, you are transmitting RF, analog waveforms. That is the RF communication is happening in the wireless medium. So what you are transmitting are basically analog waveforms, and those analog waveforms are received, they are converted into bits, they are converted into frames, they are converted into packets, they are converted into your segments, and then they are received by the application. Then you are able to communicate between the two devices, right? So your digital communication, when your digital signal needs to be modulated first, then the modulation is transmitted to the wireless media, and then we again demodulate it to convert it into a digital signal, right? So your bits are modulated, transmitted over the wireless media, and then again demodulated, right? So there are different methods of modulation here. There can be, amplitude shift keying, frequency shift keying, phase shift keying. So amplitude shift keying is actually, you're shifting the amplitudes according to the bits. For example, 0101. So the amplitude of the waveform is shifting according to the bits. Now when you're talking about frequency shift keying, so I'm shifting the frequencies according to the bits. So this is how we are modulating the carrier frequency or the analog waveform with according to the bits. And phase shift keying is I'm changing the phase of the analog signal or the carrier signal according to the bit stream. If it is 0101, so whenever 0 come, I will change the phase. I think we can have that kind of modulation, right? So this is how the modulation of the bits are done, and the bits are, modulate the carrier waveform, and the carrier waveform is transmitted through the air. Okay, now in the air or in any kind of media, there can be impairments which are added together with the waveform. So there can be attenuation. Like attenuation is that in the transmission medium, power is, reduced. It is attenuated. Then we have to use an amplifier to again amplify our signal. Then there can be distortion. So distortion, as I already told, is due to the finite bandwidth of the channel. So whenever we are transmitting any signal, for example, this kind of signal, due to the components of in the media, there can be distortion in this signal due to the frequencies used. Then there can be noise. So noise, like for example, this is the transmitted waveform. Now this noise is added in the transmission medium or at the receiver side. So now this transmitted waveform has a peak here, and this peak is due to this noise. So this signal is actually added here, and it has made the received signal noisy. Right? So noise is added due to the transmission medium. So all these things or these impairments are happened in the link which is made, or the physical link which is made of the media. So there is attenuation, there is distortion, there are noise, right? And apart from these impairments, okay, let's skip all of this. So apart from these impairments, there is another important thing, that is your wireless channel, right? So your wireless channel is like a channel in the air. For example, when we are talking about a wireless communication, there will be a wireless channel. For example, this is your transmitter here and this is your receiver here, right? So it has L number of paths which this transmission will take. So it will be a direct path, then there will be some of the reflected paths here, right? So there are different number of paths here which it is going to take to form the wireless channel, and then your signal passes through that channel, and the received signal is received at your receiver passing through that channel. So this channel also adds a lot of impairments in your signal, right? And including all the impairments, that is your attenuation, distortion, noise, and the impairments of the channel, your signal is received at the receiver side, right? So now again, so let me quickly go to the slide. Yeah. So this is how your signal is. Yeah. So can you see my screen? Can you guys see my screen? Is my screen visible to all of you? Anybody can speak? Yes,
Yes, ma'am. Yes, ma'am. It's visible.
Okay. Okay, so now we have, transmitted our signal to the media. All the impairments are added in the media. And now this, let's finally see that how it has been, done. So here we had our sender. It was trying to access the Facebook, and trying to, transmit the signal. Now, this signal is transmitted using a segment, then this is converted into a packet, it is converted into a frame, it is converted into bits, it is transmitted as a, as signals. Now this is transmitted to a media, this is converted into a received signal, it is received, and your signal is, received as a signal, it is converted into bits again, it is converted into frame again, then packet, then segment, and it is then received by the receiver. Now, when we are talking about the media, you guys want me to delve into the wireless channel or not? You have to tell it to me, or, is it okay to leave it up to that how this channel works? So basically, the channel adds a lot of, we have talked about the impairments, but the channel in itself is a huge topic, and we can actually delve into it, that how, in the channel, these waveforms travel, and how these waveforms are received at the receiver, and how they are reconstructed, and this kind of received signal is received. You want me to go into the details of that? You can say yes or no, or we can just finish it over here. We can actually look into how these um, signals are transmitted and received. If not, then I will just stop here, and I'm open to all the questions you have. And if you guys want, I can delve into the wireless channel, and we can have a great experience of understanding how these waves travel in the channel. So what do you guys want?
Hello, ma'am.
Tell me. Hello.
Ma'am, can you please explain more on the receiving part of this one, ma'am, and also the error, no, the echo thing when it reflects to a wall and all those things.
Oh, you want me to explain that? Yes.
Yeah, the thing is the errors when it comes to the double error and all those things.
Sure. All right. Then if you are interested, then I'm more happy to have it explained. So let me just go back to that slide. Right. So yes. So we are looking into the wireless channel now. Is it visible to you, Sudhir?
Yes, ma'am.
Okay. So now what we have is a wireless channel, right? So we understood that we have signals, right? And we have bits. We have modulated the bits. Now bits are in the form of analog signals. Now we are transmitting those analog signals in our channel. So channel can be any type. It can be an indoor channel. It can be an outdoor channel. In any type of channel, there are paths which the analog signals will take, right? The analog signals will take certain paths, and it takes certain paths in the outdoors, right? It takes certain path in the indoors as well, right? And then only after taking the paths, it reaches the receiver side, all right? In the outdoors or in the indoors. Now, let us see. Then when we transmit a signal through the air, there can be different multipath component, right? So we had one analog signal, but now it is taking various multipaths. So we have various multipath components, right? That means the electromagnetic waves or the RF waves will get scattered by various objects, right? It gets scattered by the building here, it got scattered by the tree here, it got scattered by this house here. In the indoors also, it gets scattered by the walls, the pillars, the tables, the chairs, the mirrors, various things, right? So there will be scattering in the path. Therefore, there is not just one path, there will be multiple paths of the same signal which is received at the receiver. So it may get reflected from various objects. All right. So now when we talk about the wireless channel, it is very important to model that channel. Why is it important to model that channel? Because when I receive that signal, I want to know, I want to have that information of the channel so that I can somehow process it and somehow reconstruct my signal. If I have no knowledge of the signal and some imperfections are added to my signal, or they get actually, my signal gets scaled by those imperfections, then it is very difficult for me to receive the signal and reconstruct the signal which was transmitted, right? Because of these imperfections getting added to my signal. So therefore it is very important to model this wireless channel, right? And this wireless channel is nothing but the multipath multipath propagation which is happening in this channel. So now, Shivam, you want to say something? All right. So our aim here is to model the HT. Now, HT is the impulse response of the channel, right? If we are, sending del T is the impulse. That means it is just this impulse. If we are transmitting this impulse, so what we will get, when we are transmitting this impulse, so there are in this scenario it can take, for example, L paths, right? We are transmitting something, it can take one, 0th path, one path, second path, and similarly L number of scattered or reflected paths it will take. So we say that it takes around L paths, right? ith path, that means if we're talking about one path, we call it as ith path. For the wireless environment, each path is characterized by the delay and the attenuation, because each path will have its own attenuation and it will take its own time to receive to be received or to reach the receiver. All right, because if some reflection takes more time, it takes a longer path to receive to the receiver, so it will have its own delay, right? If it is a line of sight, if I'm transmitting and there is a receiver and there is a direct path, then it will have the lowest delay. If it is taking a longer path, it will have a higher delay, right? So each path will have different delay and have a different attenuation, right? So now these multipath propagation leads to, so now this will happen. So this is how it will have a certain, now this is what we had transmitted, this is what we have received. So what we receive, one multipath have its own attenuation and it has its own delay. Okay. So this is the delay which has happened and this is the attenuation, that means its amplitude has changed. So this represents that the system has certain attenuation AI and it has certain delay tau I, right? So it has a certain delay and has a certain attenuation. Each path. Now, when all these signals gets all these paths are received at the receiver side, okay, it further it is combined together. They are superimposed over each other at the receiver side, and when these signals are superimposed over each other coming from different paths, further leads to interference, right? All these different paths are getting superimposed, that means they are getting added to each other, then it will lead to interference, and it can be constructive or it can be destructive. Okay, so a constructive interference actually adds up together, all these paths add, or signals adds up together and amplifies the signal, have a higher power because they all are added together. But for example, if they have different phase, or somehow they have been added but having different phase is actually clashing each other and having attenuates each other and having a destructive interference. So therefore we have to model the channel in such a way that we can define it as a multipath propagation environment where the signals can have a constructive or destructive interference when they are added or superimposed at the receiver side. Now, let's talk about the multipath scenario. So, for example, we have this zeroth path. So, zeroth path will be having attenuation A naught and delay tau naught. So, attenuation is A naught and delay is like del T minus tau naught. First path is having attenuation A1 and delay tau 1. So, we can write A1 and del T minus tau 1. And similarly, L minus 1th path will have AL minus 1 attenuation and tau L minus 1 delay. Okay, so we can write the equation as AL minus 1 and del tau T minus tau L minus 1 for the L minus 1th path. So this is the multipath scenario. This is how all these paths are getting received at the receiver. So this is what we will receive, right? Zeroth path, A naught, delay tau naught. 1th path, A1 is the attenuation and delay is tau 1. So this is how the stream of multipaths we are going to receive at the receiver. Now, multipath received signal is superposition of these signals. So what will happen? Basically, they are going to get added at the receiver side. So all these, multipath signals are getting added. So this forms our channel. This forms our wireless channel where all these paths are getting added. So A naught del T minus tau naught plus A1. So these are all getting added, getting superimposed. This naturally happening. We are not doing anything, right? This is happening naturally. We are receiving it in a multipath propagation environment, and they are all getting added together. They are getting superimposed over each other, right? So we can write HT or our channel as summation of all the multipath signals. Okay? All the multipath waveforms are getting added, right? Now, so what we had transmitted, for example, we had transmitted a baseband signal ST. We had modulated it over a carrier frequency FC. Alright, so we had transmitted this signal SPT. Okay, right? Now we have the multipath scenario. Okay. And now what we have YT as this ST, which is this, and then the carrier frequency FC. So what we have received here is this now. Okay. So your AI, your ST minus tau I, that is your signal which you had transmitted. Now this has the frequency term and the phase term. Now this is your baseband signal which you had transmitted, and then you had multiplied or modulated it over the frequency, carrier frequency. So now this is the signal which you are going to receive at the receiver side, having all the multipaths which are added. Right? All the multipaths which are added. Now after demodulation, now what we will do with this received signal, we will demodulate the signal. So when we demodulate it, what is now this carrier term is gone. We have demodulated, we have removed the carrier term. Now what we have is this signal. So it has the attenuated part and the phase factor, that is the delay. Now let's see a representation how the signal is received. So it is received one by one. How the multipaths are received. This is just a demo that how the multipaths are received. See again. So this is how one by one the multipaths are getting received at the receiver side, right? And now all these multipaths are going to get added. Now when they are added together, this is what we get, this kind of waveform. And this is a typical envelope which we are going to receive. Okay. All these multipaths are coming together, they are adding over each other, and this is what we get received. This is what we get as a received envelope. Now, what we have this YT. We have this demodulated form of this YT, which has the attenuation and the phase factor. Phase factor is due to your channel. Multipath components of the channel are now AI and tau I as it was there. So this is AI and this is your tau I. So it has attenuation factor and the phase factor with it. Now, for example, if this is your A0, A1, right? And your A0 and A1 is equal to 1, which is your attenuation, and your tau naught is equal to, suppose these are L is just equal to 2, only two multipaths, right? A0 A1 is equal to 1, tau naught is 0, and tau 1 is 1 upon 2fc. So when we put these values into this channel, what we get is yt is equal to hst is equal to 0. That means these two multipaths have cancelled each other. And this is a form of destructive interference, right? This is a form of destructive interference that these two multipaths have cancelled each other and no signal is received. This is a form of destructive interference. It happens automatically. We don't have any control over the wireless channel, right? This is the point. Media, we don't have the control. Now, if your tau naught is equal to 0 and tau 1 is equal to 1 upon fc. When we put these values in here in the channel, what we get is yt is equal to twice of st. St is your transmitted signal. That means your signal, transmitted signal st is now amplified to twice. So this is one example of constructive interference where two multipaths have added to each other, right? They have added to each other to form a constructive interference. Now, these are two examples of constructive and destructive interference. Now, for that, we will have to have, a probability distribution of H in order to understand that how this H is actually, performing and how this H is actually going to behave. So this H is basically not deterministic. No, it is random. It is random because why? Because, this H keeps changing. H keeps changing how? Because this is a wireless channel. If certain environment around your thing changes, or you follow some other path or you go some other way. So this is basically a random quantity. So any random quantity doesn't have any particular value, but it has its probability distribution. So we are going to find out the probability distribution of H in order to understand that when we are going to transmit our signal, how this H is going to behave, right, on our signal and what we are expecting at the receiver, right? So, so now we had H here, right? We have H here. This is our channel. Now this H we can write this using a Euler's formula. We can write it in the form of sine and cos, right? We can write it in the form of sine and cos, and then we can write it as x, and this one as y. Now x and y are sum of large number of components. These are sum of large number of components, that is the nth components, or involving ai and tau I, that is the attenuation and delay of each path. Now when ai and tau I both are random in nature, it can be, they are random. Any time delay or any attenuation can happen in the wireless path. Now, using the central limit theorem, what we know that when we are adding large number of independent random variables, the sum tends towards Gaussian random variable, right? So when we are adding such large number of independent random variable, any type of random variable, when we add in large sums, it tends towards a Gaussian random variable. So from this, we can say that our x and y will be Gaussian distributed in nature. So this is a form of Gaussian distribution. Our x and y both will be Gaussian distributed, having a mean of mu and variance of sigma square. Now, so x and y both are Gaussian distributed in nature. We assume that they are independent Gaussian random variable having mu or mean equal to 0 and variance of half each, so that the overall variance becomes 1, right? So when we write the joint distribution of both of these, we know that they are independent, so we can write the joint distribution of x and y, xy, as f of x, that is the frequent probability distribution of x, and probability distribution of y, which can be given as this. Now, this is the characterization of the feeding channel in terms of real and imaginary parts. So basically, we are doing the characterization of x and y, which is actually the real and the imaginary part. But what we want the characterization in terms of the attenuation and delay, because we are interested in the attenuation, and attenuation will give us the signal power, and delay will give us the phase of the signal. And we are interested in the power and the phase of the signal, of the received signal, right? So this is the channel, this is the amplitude and the phase. So we are writing the channel in terms of x plus jy, right? And we can write it in this way. And this is the amplitude and phase. Amplitude will be the amplitude of x square plus y square ka whole under root, and the phase will be tan inverse of y by x, right? We can write in this way, where x is a cos phi and y is a sin phi. Okay, so we have written the real and imaginary part in terms of amplitude and phase. Now we want the characterization of the amplitude and phase, which will give us power and the phase of the signal, in which we are interested in. Now from the joint distribution of the real and imaginary part, that is x and y, we can derive the joint distribution of A and phi, that is your attenuation and phase. This is a simple translation. In mathematics, you can do from the joint distribution of x and y, you can calculate the joint distribution of A and phi, because we know the relation between them. Now, from the joint distribution of A and phi, you can calculate the marginal distributions of A. So this is a distribution of A, your amplitude or your attenuation, right? And this is actually known as Rayleigh distribution. So basically, the signal power which you are going to receive through this channel will be Rayleigh distributed. All right, this shows the signal is Rayleigh faded, or the signal is going to get Rayleigh distributed. All right, so let's look at what is a Rayleigh distribution. So Rayleigh distribution of the signal amplitude A is given here. So this shows that there is a low probability that the signal amplitude is having high values. So there is very low probability that the signal which you have transmitted has very high values. It has very low probability that the value of A, amplitude will be 3 or 4 or higher. Right? Now, it has a very low probability that the signal takes very low value close to 0. So this probability is also less that your signal will have very small values, right? So it is this small values called as deep fade. So it has very low probability that the signal will be deeply faded, right? And there is a high probability your signal will take the values from 0.75 to 7.25. So this has a very high probability, and this region also has a high probability, right? That it will take values from 0.2 to 1 and 1 to 2. Right? So this is a higher probability region. All the values in the Rayleigh faded area will take values here. All the signals will take values here, right? So what is important in a PDF is that it is how the values are close to 0. So we don't want a PDF to be very close to 0, right? Many values close to 0, which will tell us that it will be deeply faded. Now, if the magnitude is close to 0, it means the signal will be highly attenuated. So we don't want it to be very deeply faded. So this wireless channel is a Rayleigh distribution. So it has many values which are, which has a higher probability in the middle region. Now, again, the phase factor, when we calculate the phase from the joint distribution, we can calculate the marginal distribution, and we know that the phase is actually uniform, is actually a uniform distribution. It is uniformly distributed from minus pi to pi. When you calculate that, we can calculate that the phase is uniformly distributed from minus pi to pi, and because of this uniform distribution, we can actually see that there might happen a destructive interference, because the phase is going to change, which is actually going to affect the interference at the receiver side. So whenever there is a phase change, there are opposite phases of the two multipaths, they are going to cancel each other. So since it is uniformly distributed, there might be instances that the signals may cancel each other. Okay, so this is how so let's skip this. So now we have understood that how the power is going to get received. So this is the yellow line is actually the power which we are receiving in the relay faded channel. Like if our scenario of a channel is relay faded, this is the kind of power envelope which we are going to receive in all the signals, all the multipaths are getting added. So there could be a destructive interference. Then destructive interference causes this amplitude to go down here. This deep fade, right? These amplitudes to go down. When there is a constructive interference, they are getting added, and we are getting high peaks, right? So this is the kind of amplitude which we are going to receive in the relay faded environment. All right, so and this blue one is actually a Russian faded environment. It is a different kind of a channel which has also a line of sight propagation in addition to the diffused multipath scattering. So the result, it results in a smaller variation since there is a strong line of sight component. So it does not have such deep fades as compared to the relay. So these are the two different channels. So this does not have such highly deep fade points here. So it has a smaller variation in the path gain. So this channel is better to in terms of transmission. We can have very effective communication if we are transmitting in a relay fading environment. So now, so when we compare it, we can see that the magnitude actually fluctuates over 10 dB in here. It actually fluctuates in between 10 dB, and the relay fading, actually fluctuates from 30 to 40 dB. This is kind of the fluctuation in the signal which we are going to receive in the relay faded environment. All right. So yeah, so this is about the channel which we are, which we have to use to transmit the signal in the wireless environment. So this was about the channel, and then so again we can have a recap, like what we had transmitted, how it has followed the path, and it has been received at the receiver side, right? So the sender. So anybody has any doubt here in the channel? I'm happy to discussion on that. Anybody has any doubt in the wireless channel? Is it clear to you, or if you have any issues here, anything is not clear, can discuss. Nothing is clear. It was very conceptual. Probably it requires a little bit of background to understand how the channel works. But since a few have asked, so I thought of explaining it in bit detail.
Madam, can I speak, ma'am?
Yes, sure.
Ma'am, it was very detailed, ma'am, and it was very informative. I joined a bit late because of the internet issues. If you had touched upon the block diagram of receiver and transmitter, it's okay that you can leave it. If you have not touched about, you can just have a small explain about the receiver and the transmitter side of the block diagram. If you have that slide, if you have any slide like that, you can just touch upon that.
Sure. Actually, I haven't touched more on the transmitter and receiver side because I was trying to explain how the information flows in the communication link, and I was not very keen to explain the physical layer, and the transmission and reception is transmission and reception block diagrams are basically the physical layer part. And I was explaining through like how the data flows from the application to from the application of the sender to the application of the receiver. But as you said, I can probably articulate it in few sentences, but I don't have any slide right now with me. So basically in the transmitter side, what we have is bits, right? So when we are talking about bits and when we are talking about transmitting it through the channel or through any medium, what we have to do, we have to convert those bits into signals, right? So when we have, or if suppose we have any analog signal with us and we want to transmit that signal, right, in any form. So what we have to do, we have to, if we have any analog signal, what we do is we sample it, we quantize it, we encode it in the form of bits. Then these bits are modulated, using pulse modulation for any wired media. We modulate it in the form of pulses, and then we transmit it. If it is, and there are different kind of coding schemes used for those, kind of transmissions over the guided media. But when we are talking about unguided media like air, and we have, a stream of bits, now these stream of bits must be modulated. When these stream of bits are modulated using the modulation schemes like ASK, PSK, QAM, whatever, then they are converted into analog signals, right? Now, before converting or modulating these bits into the analog signals, let me try to actually show that to you. Okay, so when we are actually talking about the bits, converting into an analog signal, what we do is we go source encoding. We do, channel encoding. Source encoding and channel encoding is done to, remove the redundant bits, add the parity bits to it to have, forward error correction. So all these things are done, and then these bits are basically the source coded. Error control coding is done. There is a stream of bits. So error control coding is basically, you can say a checksum bits, some parity bits are added according to the error control scheme you are using, right? So all these bits make a stream of bits having, the data packet, your data having, MAC address, physical address, logical address, then your error control coding you are doing, right? Add the parity bits to it, and these, stream of bits is then, what happens, it is now this stream of bits is going to get modulated, or is going to get converted into an analog signal when you are trying. Yes, Amit, you're saying something? Okay, Amit sir, you're saying something? Yes, I will just take 2 minutes to explain
Yeah.
this, and then I will finish.
Okay,
Yes,
ma'am.
sir. Okay. So when we are talking about the stream of bits, we are going to modulate those stream of bits, which has, the error control bits, the various other MAC address, all the bits in the frame. We are going to, we are going to modulate that. So in modulation, what we do is, we modulate these bits, or these digital, or the bits into an analog signal, because the unguided media or the air only understand the analog signal. So what we will do, we will use the modulation schemes like ASK, PSK, QAM, etc., to convert those bits into the analog signals. And then these analog signals are transmitted into the air, right? So this is how it works. Am I able to make any sense to you, Sudhir?
Yes, ma'am.
Sudhir, sir?
Yes, ma'am. Yes, ma'am.
Oh, okay. Probably I will just add a few slides of the transmitter and receiver architecture to you, and then, with an explanation, a little bit of explanation in the slide, and I think that would be helpful, and I will definitely share with Dr. Amit, and he might share it with you. Is that okay?
Yes, ma'am. I knew about the transmission of wireless and all those things. I knew a thing, but I didn't know about the what do you say, the fading and these kinds of error thing. I didn't know about that. Also, I didn't know about the hardware side. So this was very clear, and it was very informative, ma'am. Thank you very much.
Thank you so much, Sudhir sir. Thank you so much. So anybody else has any doubt? So I think it is already 11, and if you have doubts, just quickly ask, and then we will just wrap it up. Does anybody has any doubt? You can ask now. Okay, then I assume that everything is clear to everybody. Amit sir?
Yeah, yes, ma'am. Yes, ma'am. Yeah,
Thank you, sir.
yeah. We can stop this session because the audience has to listen. We will have 30 minutes gap, and then we will start at 11:30 with another session. So Subha ma'am, we have to stop here.
Yeah, it's already over, sir. I think all the doubts are clear to everyone.
Yeah, yes.
So we can,
So,
we can.
thank you so much,
Thank
ma'am.
you. Thank you so much, sir. Thank you so much for inviting me.
Fine. So, audience, we will start at 11:30 with the new session after 30 minutes break.
Okay. Okay, sir. Thank you so much.
Thank you so much. Okay.
Thank you.
Baneji, we can stop recording for few minutes. Okay. Subha ma'am, we can leave now. Then another session.